So with the hockey player, we're dealing with ratios, as I said, stuff we've been doing all year, things that are valuable to you even when you're not a physics student, understanding how a change in one thing creates a change in another. All right, so we have a hockey player. He's some distance from his pal. All right, we'll call this x is equal to 0, and his teammate's over here, and we'll call that distance x. Okay? So he tries to pass it to him, yet is unsuccessful. Right? In fact, the distance that it actually goes, delta x is actually 1/2 x. Okay? So if he gave it an initial speed of 1.7 meters per second, and it went halfway, how fast would he have to have passed it under exactly the same circumstances for it to have reached him? Okay? Does anybody have just the top off the top of your head? What do you think it is going to be? Is it twice as fast? 4 times as fast? Or 2 as fast? All right, so you guys are already getting the idea that we can't automatically assume that it's just 2 times as fast, but we're sort of understanding, because we got v squared in there, so it could be square of the distance, could be the root, square root of 2 of the distance, so times the distance. So let's see. All right, so what do we know about it if it's going some distance? What do we know about the acceleration? What do we know about the work done by the non-conservative force? All right, so when it stops, what do we know about its velocity? V is equal to 0, okay? So we have some initial kinetic energy here, and that's going to be the same in each case. The initial kinetic, well, no, that's not true. Here we have initial kinetic energy 1/2 mv squared, and over here we have a kinetic energy equals 0, okay? So the work done by what? What's doing the work here? Friction is, okay? So the work done by friction is equal to force times distance, okay? So is that a conservative or a non-conservative force? It's a non-conservative force. All right, so we'll say the work done by non-conservative force, work done by friction, is equal to FD. Actually, what is it? What mistake did I make already? Yeah, it should be negative FD, right? Because let's just think about it. We'll draw a diagram. If the velocity is in this direction and friction is acting in this direction, then the angle between them, 180 degrees, cosine of theta is equal to -1. All right, so the work done by friction is equal to negative FD, okay? And so for us, that is work done by friction is equal to negative of friction times our what? We want it to go a distance x, but it only went 1/2 x, all right? So x over 2. So that's the work done by friction, okay? So the work done by friction, if we send it the whole way, is going to be equal to, if we go all the way out here, the work done by friction is going to be equal to what? Negative Fx. All right, so where are we going from here? We know that, I haven't worked this one out, so I'm thinking about it too, all right? Okay, so here we have 1/2 mv squared has got to be equal to F times x over 2. Is that correct? Because where we started with was, here, let me do that more conventionally. We've got kinetic energy plus work done by the non-conservative force, friction, is equal to 0, because that's our new energy, right? At the end. All right, so we know that 1/2 mv naught squared, or our original velocity, is equal to F times x over 2. All right, now up here, based on the same thing, we've got, instead of 1/2 mv naught squared, we've got 1/2 mv, our new mv, all right, that's what we're solving for, squared is equal to Fx. Does that make sense? All right, so now how are we going to put this together? We're looking for a ratio. Do we get a number for how fast he passed it? Yeah, 1.7 meters per second. All right, so that is our original V. Well, let's take a look at that. We know that we want to use a 2-equation strategy, so let's set each of these two things equal to stuff, then set them equal to each other, so all that junk will go away. Does that make sense? All right, so here we could say Fx, so let's say mv naught squared is equal to fx. How did I get there? Multiplied each side by 2. All right? And over here, well, we're going to get rid of the m2 in a second. And over here in red, we have 1/2 mv squared is equal to fx. Okay? Let's divide through by m. All right? Over m. And we'll get rid of this m. And we'll get rid of this m. So we got both of these equal to fx over m. So we got v naught squared, and we have 1/2 v, both equal to fx over m. So we're going to set those equal to each other. All right? So v naught squared is equal to 1/2 v squared. Got it? All right. So now what are we trying to solve for? We're trying to solve for this v, the real v. All right? So we just multiply each side by 2, take the square root. We got v is equal to the square root of 2 times v naught squared, don't we? So v is equal to the square root of 2 times v naught. Who was it who said that, guessed that to begin with? Jason. Well done. All right? So that's just our algebraic relationship. All right, so now we say v is equal to the square root of 2 times 1.7 meters per second. So 1.4 times 1.7, bless you. 2.4? 2.4 meters per second. All right, now let's go back and look at that. And let's think about how what you've learned all year comes into play. All right, we're talking about ratios. So this is from previous. This is not even considering work and energy. We talked about ratios, so to work with the ratios, what did we end up doing? We tried to find a situation where we could set 2 equations equal to the same thing, so we could set those other sides equal to each other. It's just a 2-equation strategy. We started using it in dynamics, Newton's laws with net force. We've employed that ever since then as one of our techniques. It's a good strategy to use when you're trying to solve for stuff. I was going to say that you don't know, but that's the only thing you ever solve for. Okay? So, any questions on that one?